Okay, so I put a lot of content into this, so it's probably going to be fast, like a fire hose of information, but I'll try and cover the past, the present, and the future of what Drake Landing offers in terms of borehole thermal energy storage. So you have the history. With Drake Landing, it lasted much longer than was intended. It was originally a pilot project at a commercial scale, but really a small commercial scale, 52 homes. And after about 17 years, they started to have some maintenance issues, and they didn't have a reserve fund, but I'll get into some of the other issues they had at the end of life. And then we'll talk about how it inspired the next generation of borehole thermal energy storage. 10 years of highly monitored data. It's really an excellent scientific resource, and I was able to use that resource for a lot of my work and advancing the work in the field. So what is Drake Landing? It's a small community of 52 homes. It's just south of Calgary in a small town called Okotoks. I lived 2 blocks away from this community, and I heard about it on the radio, and I joined up with the team, and this is when I switched from the dark side of oil and gas into renewable energy. And my very first GeoExchange project was a borehole thermal energy project. So it's got the garages all in the back have solar thermal. It's solar thermal only. At the time, they didn't feel the heat pumps were of good enough technology to work with a heat pump system and solar. So they did solar thermal, and their target was over 90% solar heating fraction for the community. So it's a pretty straightforward borehole thermal energy storage, 144 boreholes laid out in a basically, here's one thing I contributed to that was, it was a square initially. Now you see it's not. And that was a 4% improvement on efficiency because of the closer resemblance to a sphere. So it's in series. It goes from the center out, and each borehole goes in series. We now design them in rings instead of doing the individual piping in between them. It gives us more control over the system. But you basically have that thermocline from the core to the periphery, and then you reverse it when you're trying to extract the heat out of it. And this is what the whole system looks like with the borehole storage. It's got 2 large short-term thermal energy storage tanks, and then it's got the house equipment where they distribute the heat to the houses, and of course the solar thermal collector array. And no heat pumps, but we'll see why heat pumps would be a good idea later. So this is a really impressive thing. So they modeled it with Transys. We still use a variant of this Type 557 duct storage thermal model. It was developed by Göran Hellström out of Sweden and perfected, I think, by Jeff Thornton at Thermal Energy Storage Systems. They predicted that they would get, I think the prediction was 45%. Round trip efficiency going in and out of the storage. It's a high temperature storage, so it runs from 35 Celsius up to 80 Celsius. So at 80 Celsius and the ground next door is 8, you can imagine there's a high loss rate out of the storage. And yet they predicted 45%. Because it's solar thermal, it's free energy. But still, 45% means you had to build a lot more solar thermal. You had to build a larger field. That's a lot of losses to deal with. But that's what they predicted with the model. They did a little bit of calibration initially in 2007, 2008. And then when they measured it, they got very, very close to that. It bounced around the 45%. So it's very impressive that you can model that and predict it from the calibration. This is the loads on the houses. So you can see it through the winter. There's quite a variance between each house, even though they're all basically the same size house, the same code, everything. And yet, there's a massive variation between each of the houses, and so you have to deal with that. The short-term thermal energy storage tanks handled that variance. This is showing the energy in on the bottom and energy out on the top, and you can see that ratio of about 45%. So what's happening in the first year there, you'll see obviously like everything's going in. Well, it was cold, and you're trying to raise it up. At 35 Celsius, it was empty. So you start at 8, and you're empty, 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 and eventually you get a little bit of heat in it, and then you reach what they call periodic steady state about year 4. That's when it starts, and then it just cycles around that temperature year over year. You put in more than you take out, but it's the same amount after that. And some years, there's just load and weather differences there in terms of why it's different each year. This is what it cost. I've scaled the costs up to today dollars. It was an experimental project, so there's lots of instrumentation that you wouldn't need on an ordinary project, but still very expensive when you're talking 52 homes. Clearly, it's a research and development project, but the value of that research has gone worldwide, internationally, and it is the inspiration for my entire career. That's how I got into all the renewable energy and the specialization in borehole thermal energy storage. So there you go. This is what the thermal cycle is over 10 years of measured data. So you can see that first couple years just building up, and then it just cycles back and forth across the temperature regimes. The very high bar is what you would inject the heat temperature. So you'd inject at 80 Celsius, and at the low bar is when you're pulling it out. That's how cold it could get. But the red is kind of the soil average temperature between the boreholes. I know I'm going very fast here, but this is a really interesting graph. This is really the meat of your efficiency and the success of your design in borehole thermal energy storage. So if you can get this to be higher in efficiency, then you've achieved your objective. And you can see those numbers. I'm not sure you can read them, but it's somewhere between 45, sometimes 55. I think some of the higher ones may be like leftover energy from the charge cycle of the last year, or it's just you have an easy year and then a hard year and back to an easy year. So then it looks like the next year was really efficient. That's I would just smooth those out and say 45%. So what happened at the end? At 17 years in, they had no reserve fund. One of the things that happened in 2007, anyone know what happened in 2008? Well, the gas prices went way down, so they had no ability to build up a reserve fund. They didn't plan for that, so that's one of the key takeaways. And so things started to break down. A solar thermal collector at 17 years mark, 20-year mark, some of the connectors failed. They made a big deal out of this, but really it was just some O-rings. For $200,000, they could have replaced all the O-rings in the entire system. They would have had that problem solved. But the proponents really weren't interested in continuing to run it unless they could get a nice additional gravy train from the government. And the government was saying, look, for $2 million, we could do another project. We'll do something different. What would that have looked like? I did one of the initial studies. I proposed the study. Natural Resources Canada also proposed a very similar approach. And we were 1 day away from everybody, the town, the proponent, the operations and maintenance operator, and the company I was with then was Stantec, and we were going to put this study together, look at these two options. These are the two options that I now put forward elsewhere, but they said, nope, we don't want to do this anymore. We're a gas company, we're just going to put gas back in, and we're going to avoid the additional costs of doing another 15 years of this. But in fact, if they'd have done that, it's not that much more to have recovered it. And when you look at it from a fresh start on Drake Landing, that's what the future would look like. So what did they identify in terms of those issues? You want to make sure you've addressed your long-term planning. You've got a maintenance plan. You've got a end of life for each component in your system so that you can replace that with the next generation of equipment, which would have been much better. They would have gone from solar thermal to PV thermal, which would have given them a lot more electricity. They would have added heat pumps, and that would have saved them a lot. So with the solar thermal, if they had had heat pumps, they could have had 1/6 the amount of solar input into the system. So that's a huge change in what it would have taken. So they identified a few issues. Those were actually resolvable. They could have done some different things. And what ended up happening is they abandoned it, said, look, let's just decommission it. They had, by environmental standards, you have to fill all those boreholes with cement. So they have destroyed that field. But in the 17 or 18 years of operation, I think it was actually only a couple of years ago that they finally filled up the holes. But that information that we got from a scientific basis, it was only planned for 4 years initially, and it ran for all these additional years. That information is priceless and is fed into a number of additional studies as well as future projects. So we do not consider it a failure by any stretch. It was a blazing success and is still taught and talked about in borehole thermal energy storage. So what would it look like if we'd have done Drake Landing today with what we've learned from Drake Landing? So we would have made it hybrid, we would have added different technologies, and we would have optimized the combination of those technologies to fit with the load profile, the climate, and the situation at the site. So here's Drake Landing back in 2007, bunch of other different places across the world. We've sited over, I think we're at 56 of these underground thermal energy storage demonstrations, or these are, it's beyond technology readiness level 9. This is clearly commercial market phase. U.S. military did a huge installation down in Albany, Georgia. 5 of their sites that were going to be geo-exchanged, they converted to borehole thermal energy storage, and all of this hinges on the learnings we pick up from Drake Landing. And of course, it's shared across the world, back and forth. We learned from Europe, we learned from, there's lots of leaders in the world in borehole thermal energy storage. So here's one of the slides we use when we're telling people the difference. Why would you use borehole thermal energy storage? Well, where does your peak power come from? What causes peak power? It's cooling in summer, and it's heating in the winter. So in Quebec, we have 2 spikes a day, heating in the winter, also in the US Northeast, and then in Ontario, it's cooling in the summer. So do you want to use $5 a kilowatt hour borehole thermal energy storage or $350 a kilowatt hour battery storage? So the different purposes, battery storage has a place, but if you want to do seasonal storage, this is the best. So this is a demonstration of what the hybrid design would look like. I hope it would work. So for example, if you had an apartment complex, these apartment buildings that we look at are roughly the same energy load size as Drake Landing. We like to go bigger. Bigger is better. I can show you why that is coming up. Here's a photovoltaic thermal. We'll collect the electricity first, but then why waste that heat on the backside? There's another 80% or 75% of the sun's energy you're not collecting. Plus, this one is finned and uninsulated. You can collect from the air. So you run glycol through it, you lower your temperature, and you suck heat out of the air and from the sun. Take that heat in the summer. We're going to drive it down into the ground. This is Drake Landing. This is the same concept. Put it into the ground. You've got a distribution of rings of boreholes in this case. You charge your core first. I think I've got the cooling one up. I slipped on the slide. It's supposed to be the heating one, but just showing you, pretend that blue is red. There we go. So we would run it up from 5 Celsius all the way up to 45 Celsius. Here we go. Oh, maybe it was just showing you the end of winter. We get it down to 5. Here we go. We're coming up. We can do passive charging out of the solar up to about 20 degrees, but because they're uninsulated, it's better if we use the heat pump and we suck heat out of the solar and push it into the bore field. When we do that, we get 5 times the energy out of the solar thermal. So that's a huge reduction in your capital cost on your solar thermal, and of course you still have enough energy to balance out your field. Balance is a key word because with geo-exchange, you're doing heating and cooling. If your loads aren't balanced, well, you can't do all your heating or you can't do all your cooling. In borehole thermal energy storage, we create that balance artificially. We add the heat that we need, or we add the cold that we need to make sure that we're balanced every year, or in fact, we put in a little extra so that when we're in a heating mode, we can manage all the losses. So we would match our extra to the losses, and we raise that temperature so that we can get more efficient. Just watching my time, I think I'm okay. So what are the levers we want to use in a hybrid geostorage system? You have to have a heat source. It could be PV thermal. Sometimes it's better if we use air source heat pumps. So depending upon your market, your tariff structure, if you have a flat electrical price, that's even if it's low, 8 cents, 7 cents a kilowatt hour, it's still better to use PV thermal because that waste heat is free and you're getting the electrical energy. But if you've got a varying spot price and you can go negative price, or you've got excess wind in the Netherlands, or you've got excess solar in California, then you can harness negative or zero or low prices and use your air source heat pumps to charge your field in the summer. And that's by far cheaper than running any photovoltaic thermal if you have the right electrical structure. And of course, you need your borehole thermal energy storage. That's what harnesses it both daily and through the seasons. So we use a combination heat pump. So we do a combination air source and water source. And what that does is it allows us to eliminate having two pieces of equipment. We double it up. We use the air source heat pump to meet the load directly. Typically we size for about 55% of the heating load to be covered by the air source heat pump. And the rest we're going to pick up when the air source heat pump is inefficient when it's cold outside, or it's inoperable because it's really cold. We live in Canada. So there are times when you can't use the air source heat pump at all. That's when we use the ground source and use the storage. So the storage will cover somewhere between 30 and 40% of your load in an optimal system. So what would it look like if we'd have done a hybrid retrofit, or if we'd just done Drake Landing 3.0 is what I like to call it, because we've definitely gone beyond 2.0 already. If we'd have done that from the start, what would we do differently? So we'd have this hybrid system. What were the other things we learned from Drake Landing? The scale. When you change that scale, just by doubling your scale, you drop your surface area to volume ratio. So now you've got a bigger storage, but it's got much less surface area per unit volume. When we do that, we lower those losses. So instead of 45%, if we'd have doubled it, I think I calculated it up to be 65%, and it was 76% if we quadruple it. And quadruple is not huge. This is 52 houses. You're talking 400 houses. What's a district system? What's a large apartment building? What is an industrial load? So by increasing that size, we did a university campus analysis in Albany, New York, 96% round trip efficiency. So that's where borehole thermal energy storage can go. And that's those two things. You want to hybridize it, and then you want to increase your scale. So here's some of the costs. That $6 million is actually wrong. That's that includes a bunch of other costs. It's actually, if we did the version 3.0, it's 1.2 million instead of the equivalent price of. It's not the 6 million. That includes the district network to the houses. So if we just look at the energy system, it's about 4.6 million in today dollars from the original Drake Landing. With what we learned, it's 1.2 million. So that's a pretty impressive learning and research takeaway from that project. So we're not at all worried about the success of it. It's definitely a success. It taught us what we need to do to deploy this en masse. And what we found is, depending upon your tariff structure, where you are in your province, your state, or your country, this already can beat the status quo. It definitely beats GeoExchange every time. We're about 40% lower capital cost and 40% more efficient than GeoExchange. And in the right tariff structure, like Halifax, for example, anything in the U.S. Northeast, we're better than boilers and chillers. So the status quo, the business as usual, is not cheaper life cycle cost-wise than this solution. So there's the scale analysis. When you look at 1, 2, and 4 times, you look at the drop in scale. And in fact, the 4 times one, I just reran the numbers this morning, and I needed to reduce the field size. So I thought it was 4,900 meters to do the 4 times. That's with just the savings in the volume area to surface. However, when you actually run it, you only need 3,300 meters. So you go way down in the cost of your bore field because you're more efficient. And so that's just the scale problem. And again, 52 houses times 4, 200 houses, it's not big. It's bigger. So difference between research scale pilot project and commercial scale economic project. So there's some of the ratios there in terms of the new version. So already, because of the hybridization, you go from 45% efficient to 60% efficient if we kept the same scale as the original Drake Landing. Then when you double the scale, 70, quadruple, 76 is probably a little better than that. And the cost would go even further down in terms of cost per unit energy delivered and the cost per storage. More lessons. I'm going to skip some of those on the retrofit. So taking the Drake Landing data that we had, and I've been working on this model for some time. Normally we use Transys and the component 557 to do this, but it doesn't cover all the different geometries. So decided to take that data and tune my own model, and that's the what I call the unified ring model. This is the ground loop design. We use a primitive geo-exchange tool to imagine that you're analyzing it. And then we use a real tool. I hope this will work. So this is the new model. Tuned the model to the Drake Landing data set. So we had 10 years of 10-minute lead data and tuned that model to within less than 1 degree Celsius and leaving water temperature on this, this new model. And the new model can do a bunch of different geometries as well. The graph in the upper left is incorrect. Just ignore that. It's actually right on the money. The graph on the right is correct. So that's the difference between measured round-trip efficiency and the model round-trip efficiency. And the new model can do all these different geometries. So if you're ever in a site where you don't have enough room, you've got a little small corner of the building, you can drill a cone in there, you could drill an inverted frustum, which I learned that geometry. And the one on the far right is what we actually consider viable for data centers. In order to drill efficiently, you keep your boreholes close together, keep your rig close, and do a directionally controlled drill, and you can get much more volume out of the same surface footprint. By doing that, we think we can actually improve the efficiency of the field. You'd think that the cylinder's your better option, but the inverted frustum is actually better than the cylinder because you get that widening of the space between your boreholes at the base, and you technically have more storage volume per unit bore length, so it's more economically efficient. So that's just showing what we can do with visualization, which is quite nice to understand how the heat flows work and to check that your model's working correctly. So what are we looking at in terms of what did Drake Landing tell us? What did it lead us to? We're looking at 4 different large markets. Data centers are definitely one of them, data center cooling, district energy networks, industrial process heat, ideally at the lower temperatures. We like to start there. That's the low-hanging fruit would be the term we want to cover there. But in Canada and other countries, for example, grain drying is a huge load. In Manitoba and Ontario, they use propane for grain drying. It's incredibly expensive, and this would be a perfect application for an industrial process like that. Mine heating is another one. Very big air loads. They have to keep it above freezing all winter, and it's very expensive. Buildings is still, as you saw all the presentations today, 30 to 45 to 50% of your carbon footprint is your building heat. And why are we heating something that's 20 degrees Celsius with a high enthalpy, high exergy natural gas? That doesn't make sense when we can do this much more efficiently. So those are some major markets. In Canada alone, those markets are over 80 billion in terms of retrofit to decarbonize. So I have time, 2 minutes for questions.
Yes, thank you, James. It's really good that you really advanced from the first Drake's Landing project. It's really excellent to see what actually you also learned beside the project, and even after it stops, you're still advancing.
Still learning. And still using the data.
And still using. Do we have some questions?
Just curious if you, like we know about thermal conductivity in different kinds of rock sources. I'm just wondering from the application here if there's a preference of rock material that you're actually drilling through or using for conductivity.
Yeah, so it's a little less sensitive than typical geo-exchange. So geo-exchange, if you have low conductivity, that's just really bad for you. In the borehole thermal energy storage case, yeah, it's bad to get the heat out, but it also doesn't lose at the periphery. So low conductivity, we get some higher round-trip efficiencies, but we still have found we prefer the high conductivity rocks because our challenge, because we now make the field smaller, so now we don't have enough surface area to get the heat out during the peak times. So we'd rather have high conductivity rock, and we focus on the borehole heat exchangers to make them very low resistance. That gives us our thermal power we need in the short term.
So if you have porosity with fluid in it, does that help or retard?
So with fluid flow, and that's actually one of the reasons I created this model. It has the ability to not only model Darcy flow, but detect it. So we can do an enhanced thermal response test. We can detect Darcy flow. We can measure the magnitude of the Darcy flow in the formation. And it basically goes at low Darcy flow, we can still do borehole. In the middle, it's like, well, we're almost ready to switch, and then we just switch to geo-exchange. So if you have a high flow, we'll go pure geo-exchange. Is there one more question over that way?
Just for the Drake Landing project, was there a cost for the service for the 52 homes?
There was. It was small. It was something like fixed $60 a month, which is way less than the natural gas price would have been. But they had intended it to follow up with natural gas price, but it didn't go up.
And then what was the cost to decommission the project? Just wondering.
Yeah, it was pretty significant. What they had to do is they had to take all the solar collectors off the roof and they had to re-roof all the garages. So because they didn't maintain the O-rings, they leaked glycol on various garage roofs. They could have paid to replace the O-rings. That would have been cheaper. And even then, if you had replaced it, you would have had a protected roof underneath. It should have been okay if you hadn't leaked on it. But yeah, it was over like $2 million or $3 million to take everything and decommission it. And our estimates were, well, I did one for 2.2 million, and Natural Resources Canada did somewhere in the 3 million range. We would have had it for another 25 years. So why? Is there any? That's it? All right, thank you.
Yes, thank you.